we're going to be looking at gravitational fields. Gravitational fields are due to objects with mass. That means in the space surrounding objects with mass, a gravitational field is created. The definition of gravitational field strength at a point is the force exerted per unit mass that is placed at that point, and a unit mass being a 1 kg mass. From the definition, we can get an equation for gravitational field strength, which is equal to the force F divided by the mass m. The units of gravitational field strength comes from its definition. So from the equation, its units will equal the units of force, which is newtons, divided by the units of mass, which is kg. So its units are the newtons per kg. Gravitational field strength is a vector quantity, so it has direction, and that is towards the centre of the mass. So near the Earth's surface, the gravitational field is uniform. So this is indicated by the gravitational field lines being parallel and equally spaced. And you can see they're acting towards the Earth, indicating that the gravitational field is attractive. So near the Earth's surface, the gravitational field strength is 9.8 newtons per kg. So that means for every 1 kg mass that is placed near the Earth's surface, it will experience a gravitational force due to Earth of 9.8 newtons. The gravitational field strength for a point mass, and that is a mass with 0 size, is given by this equation, where m is the mass of the object and r is the distance away from the centre of the mass, and g is the universal gravitational constant. It's important to note that the gravitational field strength obeys an inverse square law with distance, and the minus sign indicates that the gravitational field strength acts towards the centre of the mass. Newton's law of gravitation looks at the gravitational force between two objects with mass, and the law states that the gravitational force between two masses m1 and m2, whose centre of masses are separated by distance r, is directly proportional to the product of the masses and is inversely proportional to the square of the distance apart. This law can be expressed mathematically by this equation, where again g is the universal gravitational constant. So you can see that the force F is directly proportional to the product of the masses, that is m1 times m2. And you can see that the force obeys an inverse square law with the distance. So the masses exert equal and opposite forces on each other, thus obeying Newton's third law of motion. And the force is always negative, implying that the forces act towards the centre of the masses, and so the masses are always attracted to each other. What you should note is that m2 is in the gravitational field of m1, and so we can determine the gravitational field strength due to m1 at point where m2 is, and that is if we go back to our definition of gravitational field strength, which is force per unit mass placed at that point. So the mass that is placed at the point is m2, so the gravitational field strength due to m1 is equal to the force divided by mass m2. The force acting on m2 due to m1 is given by Newton's law of gravitation, and if we substitute for force F into the equation for gravitational field strength, that will give us then that the gravitational field strength due to m1 is equal to minus g times by m1 divided by r squared. Also, mass m1 is in the gravitational field of m2, so we can then determine the gravitational field strength due to m2 at the point where m1 is. Gravitational field strength is the force per unit mass, so at that point the mass is m1, and the gravitational force acting on m1 due to m2 is given by Newton's law of gravitation. So if we substitute for the force F into the equation for gravitational field strength, we get then that the gravitational field strength due to m2 equals minus gm2 divided by r squared. So these equations are showing you the gravitational field strengths for masses m1 and m2, and even though m1 and m2 are different and their gravitational field strengths are different, they will still exert the same gravitational forces on each other.